All right, so this video is just going to be a discussion of the Playlist Blender web app and in particular its development. Um, I just wanted to create this video just sort of as behind the scenes of this web app that I recently completed. The sections that this video will be broken into are the introduction, the technologies I used in the video, the basic setup, or not so basic depending on how you look at it, the blending algorithms themselves, and also just some personal stuff, including what went well in the project and what I'd like to improve on in future projects of my own. Basically, this video is directed at any others who are interested in creating like a similar type of app involving maybe APIs, authentication, or working with large data sets. Basically, just showing some of the techniques that I used. I think it's nice to see what's really going on in the code behind a project rather than just seeing the project at its face value. Um, as a side note, I would suggest not getting bogged down in some of the specific code snippets that I show. Looking at a finalized application like this can sometimes get you overwhelmed, or at least it can for me. Even when I look at the code that I wrote for this app, it can be overwhelming to trace it all. So look at the code snippets if you feel like it, but the main thing is, it's better to just get the general gist. And just another side note is that some of the terminology I use throughout this video does assume some prior exposure to programming topics, but don't worry if you don't recognize some of what I am discussing. The technologies I used throughout this project include Vue, which I use as my front end framework, even though this wasn't a front end heavy app, Bootstrap for stylistic purposes, the Spotify and YouTube APIs. Most of my code, though, I did just write in plain vanilla JavaScript. All right, now just to get to the setup, some of the more tedious and boring parts of it, but important nevertheless. So I did have to learn the basics of what's called OAuth verification, which is a very standard verification procedure used over the web for linking APIs. And I had to register my app to get it verified with Spotify and YouTube so that I could use the APIs to get access to sensitive user data. Google is a bit stricter with allowing developers to access user data, so with the YouTube API, I actually had a sort of long verification process that I had to follow. Now, how the app is actually connected to user accounts involved a pretty similar process for both APIs. Basically, to summarize, once a user logs in to their Spotify or YouTube account, they're then redirected back to the Playlist Blender app with an access token appended to the redirect URL that they are now in. So with this access token, the Playlist Blender app will basically extract it and store it temporarily, using it for any API requests. Also, despite this being a small app, I still decided to create a centralized store, which you might refer to as state management, just in order to keep track of user data and user input into the app. I just wanted a sort of global store where all the information we need to blend the playlists is stored, rather than just trying to access the information from each of the individual components once it's time to blend. It's just nice to have this global store. Now, note that all of this data is stored temporarily. I don't actually store any user data in a database. And I really just created this store, like I make it sound like it's something complex, but I really just use a separate file with an object to contain the components of this store. This object is read only. And there are third party state management tools such as Vuex or Redux if you've used React, but it felt a bit overboard to kind of go on that train here. So, anyways, the final thing in the setup I wanted to discuss was just how I actually handled API requests throughout my program. Now, the API requests I was making in this program are pretty platform independent. So, what I mean by that is like, some of my requests would be things such as retrieving the playlist a user has or creating a new playlist for a user. Now, whether you're on Spotify, YouTube, or another user platform, we all need those same requests for this app to work. So semantically, we're making the same requests, whether we're creating a playlist or whatnot, but we're just using different platforms. So the actual implementation of these requests is certainly a bit different for each platform. But this really just seemed like a perfect case where we could create an API engine superclass, calling it an API engine. You could call it an API interface, whatever. But this engine will handle all API requests with specific implementations for each platform. So, like, for example, if we need to make a bunch of Spotify requests to a particular account, we instantiate a Spotify engine that we use to make and parse those requests. Now, just a bit of explanation of why I actually decided to go ahead and create a separate class rather than just making the API calls when they're needed. Well, one reason, an object-oriented principle known as encapsulation, it just made more sense to create one body, one encapsulated body that is, from which all requests could be created. Additionally, just general separation of code. It's just nice to keep track of API requests in like a separate entity, this case being a class. Part of the reason I decided to abstract the stuff into a class is, well, just that. Like I was noticing similarities in my code, when I was making these requests, and I'm like, all right, let's abstract this. Whenever I notice similarities, or I at least do my best to try to abstract things into a some sort of more general purpose solution like a class in order to just simplify the code. And I noticed that most of the API requests here I was using have like a similar outline or scaffolding, if you will. I was using the fetch library, which is native to JavaScript. So just as a side note, I used a pretty awesome tester app called Postman just to play around with some of the API requests before I like full on went into making this app, just to see if the API requests like I was making were viable. So I highly suggest Postman. The video is not sponsored or anything, but I thought it was a pretty nice application. So I already sort of went over this. So next, I'm just going to discuss the fun stuff, the meat of the application, which was the blending algorithms themselves. So, I'm going to start basically this section more generally describing the algorithms, and then as the section moves forward, we'll get more and more progressively specific into the detailed implementations of the algorithms. So, most generally, an algorithm is really just something that contains input, does some work, and generates output or side effects, if you will. And basically, the input into this algorithm was, two or more playlists of the user, and also the merging options that the user chooses from, which I'll get into in a bit. Now, the output is a new playlist. Well, the output isn't, it's not returning a new playlist, but this is a side effect of the algorithm. Basically, a new playlist on the platform that the user specifies, which contains either the common songs or the songs from the common artists or all the songs from all the playlists. So, depending on which option the user chooses, it will perform one of these three options. We're going to focus primarily on the common songs function, which is similar to the second one, songs from common artists. The third one's a bit simpler. Okay, so I'm going to start by discussing the common tracks or common songs algorithm, which essentially takes multiple playlists and proceeds to find the common songs among the playlists. So for instance here, let's say we have these three playlists, playlist 1, playlist 2, playlist 3, and let these letters represent songs in the playlist. So if we want to find the common songs among these playlists, well, there's, asking the question of taking the common songs really can go in multiple different directions. We could say, okay, get all of the common songs, or rather get songs that are common to 3 playlists, right? Which in this case there are none of. We can see there are no songs that are common to 3 playlists. Or we could ask a different question, get all the songs that are common to at least 2 playlists. So in this case, as you can see, there are songs that are common to two playlists. B is common to 1 and 2, and A is common to 1 and 3. So if we are to go in this route, which this min common variable, that's what I'm referring to. Um, that's basically the variable I'm using in my code to describe this property of the minimum number of playlists that a track must be common to in order to add it. So if min common is 2, well, we expect A and B to be produced. But if min common is 3, meaning we need to, a song needs to be common to all 3 playlists, well, unfortunately, there's no common in this case. So that's a brief introduction. Now, going back to this, the design, basically what I'm doing here is finding something that I'm calling the cross products among the given playlists of the correct size. So if you're familiar with Cartesian products, it's sort of similar to this, but I think a visual representation, again, will best show this. So let's say our min common is 2 here. Well, we want to find all of the cross products among these playlists of size 2. So for example, one cross product would be A and B, A, B. Another one would be B, 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 B. And now if for each cross product, what we'll do is look for similarities in the tracks. So in this instance, as you can see, out of all of these products, there are 2 products whose tracks are all similar, or really in this case, equivalent. So as you can see, BB, AA, those 2 cross products have all similar tracks. And so those are the ones that will be extracted into a new playlist. Now, to dive a little deeper into the implementation here, so of how we're actually, going from this step here to this step here where we're generating cross products from the playlist. Well, the first step would be to generate min common size subsets slash combinations of the playlists themselves. So what I mean by that is basically to take these playlists, right? If we have playlist 1, playlist 2, playlist 3, and then we're saying, okay, if min common is 2, then we want to be comparing every subset of size 2 that contains these playlists, not the tracks in the playlist, but the playlist. So we're saying, all right, let's match up playlist 1 and playlist 2 to compare, match up playlist 1 and playlist 3 to compare, and match up playlist 2 and playlist 3 to compare. So this is the generate subsets feature here. Now, for each one of these subsets or combinations or whatever you want to call them, we're going to compute the Cartesian product. That's where that product name comes in. So for example, playlist 1 and playlist 2, let's just do this one. Playlist 1 and playlist 2 equivalently can be written as this. Playlist 1 containing AB, playlist 2 containing B. And we're saying, okay, let's take the Cartesian product of this. If you take the Cartesian product of this, which basically means like match up every element in one array or list with the element of another array or list. So we have to match them all up. So we're saying, okay, match A with B and match B with B. Great. So now we have generated the Cartesian product of this particular subset of playlists. And then, as you can see, we go ahead and do that for the other subsets as well, giving us a list of all of the products that we need, hence the cross products. So after that, step 3 would be to, as I already discussed, analyze the products for similarity. So out of all of these products, we can see that these 2 have contained tracks that are equivalent. So we're going to use the track designated by each of these special cross products, if you will, and add that to the new playlist. So we get A and B. And of course, we actually have to do the step of creating the new playlist on the correct platform with those given tracks. So now I'm just going to briefly discuss how we actually determine if a track is in multiple playlists. So in here, it was obvious. We just said, okay, we have A here, right? And like A here. So A. Okay, obviously that's in 2 playlists. But in the practical sense, when I'm comparing tracks, oftentimes these tracks are being compared cross-platform. So the tracks themselves might actually contain like different title names or slightly different artist names or something like that. So we can't actually compare for exact equality here. We have to compare for similarity, which, you know, adds a little bit of complexity to this, but it's nothing crazy. So for example, there's a song called Leaked by Lil TJ, and on Spotify the title is Leaked, while on YouTube the title is Lil TJ dash Leaked official audio. So let's say we have to like sort of figure out, okay, these are the same songs. So here's how I do that. Basically, I use a set of various similarities, and if the I sort of like compute an overall value based on those similarities, and if this value is high enough, then I deem those tracks to be indeed the same track. So one similarity I look for is in the track name. If the names overlap, for example, or if the names are quite similar, I actually used a string library to assist with uh, like actually testing the similarity of the strings. Don't be afraid to use external libraries, by the way. um, and I also kind of looked at the artist name, which is a little bit more complicated, but seeing if the artist names overlap and if the artist names are similar. And basically, like I said, if enough of these similarities are present, then the is similar function, which I use to compare these tracks, will return true. And because we're comparing for similarity here, the algorithm works the vast majority of the time, but it can certainly have some hiccups when we are working cross-platform, which is the disadvantage of this application, but it's also what makes it unique. So to go into the next version of this algorithm, which is to extract the songs by common artists in playlists. So if we have, you know, playlists like 3 playlists and they contain a ton of artists, we're trying to find all the common artists, and then we'll take any songs in those 3 playlists that are by those common artists and add them to a new playlist. So really, it's pretty much the same sort of idea as the previous one, except with a new initial step, which is to basically extract a list of all of the artists in each of those playlists, and then determine the common artists using pretty similar methodology to common tracks. And finally, another new step is to search the playlist for any songs by these common artists. So it's kind of just adding a bit more complexity onto the previous algorithm, but I'm not going to dive into it because it's essentially pretty similar. And finally, we have something that I call the union function, because in set theory and discrete mathematics, we're essentially this algorithm is essentially taking the union of the 2 playlists, meaning it's merging all of the tracks in the playlist. So it's getting all tracks from all the playlists and then creating a new playlist with all those tracks. So the implementation is pretty simple for this one. And it took inspiration from what's known as the inclusion exclusion principle, which basically just says, okay, if we have 2 sets like this, we have to take the sum of them, right? So everything in A and everything in B, and then we have to remove the intersection once because the intersection is double counted. So basically, in the form of playlists, what this means is to concatenate the tracks in all the selected playlists and then remove any duplicates that result from this overlapping intersection. And this is a pretty good visual depiction of sort of like what it means by this overlap and how it gets counted twice, and hence we need to remove it once. So now just to get into the like efficiency part of this app, um, which, you know, we don't oftentimes have to care about like things like time complexity nowadays, but for like an app like this that is dealing with very large data sets of playlists, I did think it was important to take some time to at least, you know, try and cut out the biggest bottlenecks in terms of my efficiency, because I was noticing like there would be times when I'd run this algorithm it would take minutes. So there were improvements that I made over time. So one goal we could use here is to minimize the number of cross products that we have to analyze, while still ensuring that all the common songs or artists are extracted, but limiting the number of these cross products, making sure we're not running into like any duplicates, which I was running into in my first iterations of this program, or first versions of this program rather. So basically these duplicate products, might not seem like a big deal, but for every single product, we have to, you know, first of all, iterate over that product in order to analyze it for similarity. And then we actually have to analyze every product for track of quality and similarity. So, just by reducing the number of duplicate products that we're creating, which is completely unnecessary, we can greatly reduce or increase the efficiency of the main algorithm in this application. So I'm not really going to get like into the very specific combinatorics and pseudocode that I have written out here, comparing my original implementation to what ended up being my final implementation of this main common tracks and common artists algorithm. But like just generally explaining what this represents, I'm basically, representing the sizes of playlists, the number of playlists, and this minimum common playlist as variables. And then you can kind of walk through different, different versions of algorithms and actually count how many products that you're creating or whatever you're creating. It's a counting process. Uh, but basically, just to summarize, I'm not going to go into each of the individual steps and their associated counts. But what I will say is that this first implementation I had resulted in s to the n times n choose m total products, while this one resulted in s to the m times n choose m products, which was very interesting to me. And it was a very subtle distinction. Like when I initially looked at these two algorithms, I was like, they seem pretty similar. Like how's one resulting in a lower number of duplicate products that is, but indeed this final implementation was resulting in a lower number of duplicates as long as m was less than n, meaning the user selected a minimum number of playlists for a track to be common to be less than the total number of playlists. So like overall, this final algorithm was going to be faster. And here's just, if you want to look like a further kind of explanation of why that first algorithm is inefficient, in that it resulted in counting products twice or duplicating products unnecessarily. But yeah, there's a little bit of other time complexity or efficiency areas that I probably could have improved on, but like it didn't really make sense to sort these playlists in order to search for them faster, just because you're only searching through them once. So I kind of just used the built-in linear search methods that JavaScript provides. And yeah, I'm not going to get into that, but all right, so I know that section was sort of long, so now I'm going to get into a bit easier of a section to discuss, which is like personal development and how this project kind of helped me as a developer and some lessons that I took away. So a general lesson that I took away when creating this project, which is one that I've already been practicing for some time, but like this kind of really hammered it down, is this general computer science or software engineering idea of breaking large problems into progressively smaller problems. There's really like no way I would have been able to create this app without at least recognizing this as part of the process, especially since when working on like a relatively large project, not that this one is, but you'll continually encounter more small problems than you expected as you go through that program. So my first CS class actually, or my first major introductory computer science class, was taught in a functional programming language, which to put simply means that every piece of your code is essentially a function. So I got really used to this process of just creating like a function and then a helper function to assist with that one, and then another helper function, and just breaking things down into smaller and smaller problems. And making this app certainly made me appreciate this process and the fact that there isn't some like magical force that's just putting programs together. Everything really is just like a big problem broken into subproblems, and that's it when it comes down to it, even if those problems might be complex. Now, if you keep your project structured well and have diligence to complete all those small subproblems, this is really empowering because it makes it feel like, anything can sort of be possible with programming. Obviously there's a lot of hurdles you'll encounter, but this, just having this mindset can help a lot. Another thing that went well was just those performance improvements that I went over. I was taking CS50 from Harvard, and during the algorithm section of that, they were discussing a little bit about optimization and runtime. So I was glad I was able to apply that to this app, along with some the combinatorics that I learned in my discrete mathematics class. Um, Another thing that went well is just sticking with it. Like I didn't try and hammer this all out in like a week or something crazy like that. Like I just stuck with it for a couple months, just chipped at it over time. And since I had like the drive to finish this app because I thought it was cool, I had a good reason for completing it, and I was able to space out the project over time and still stick with it. Now, some future improvements and critiques of my own habits or development processes during this app was, first and foremost, I'd say testing my code properly. And what I'm really referring to here is unit tests, not manual testing. Pre-creating tests that you can run for each of your individual functions. Like at first I was kind of just like, I'll just bypass testing. I'm going to be learning about it in the future. But honestly, I think I would have benefited massively from testing individual functions rather than trying to trace everything down with print statements and debuggers. And it got really consuming rerunning the algorithm like what felt like millions of times with a variety of print statements. And yeah, part of the difficulty here is that I'm just simply don't really know how to test well in a language like JavaScript. I've only really had experience testing in a functional programming language. Another big thing was just like finding in the future, I really want to find ways to receive more in-person feedback. Like code is great in that it does give you direct feedback via like any errors you might run into, but your compiler is not going to talk to you about program design. So ideally, I'm going to find ways to get other people to look at my code, or I can look at other people's code and whatever, just to get better with program design. I'm starting something soon that might assist with that. Another thing is just like properly planning everything. I'm a huge advocate of planning, and I think I could have done a bit better here, even though I did draw out some diagrams. So in the future, I might make that process more robust. Another thing which I also really value is proper commenting, because it can help you, at least for me, I found it very much organizes my thinking. But I don't really have a solid commenting process down yet, and in the future I just want to kind of develop my own commenting style mixed with widely used conventions, but just for documentation of functions and classes to do a bit better of a job with that. And finally, my error handling in this program. It's just something I'm not very experienced in. Again, and I had like a sort of global error handler where I just take like any errors from the application and display them to the user, but I didn't really deal with edge cases or any specific error handling, which, some of these error messages that users could be receiving could be confusing. So finally, just to conclude, this was certainly a fun app to make, even though it could be a little difficult and frustrating at times. That's just kind of how these things go. I can see like how a video like this could possibly like intimidate a beginner, especially since I was rambling a lot. But like for novice programmers, it's probably just better to like work on small projects. This wasn't a ridiculously big project, but like, if you're just like starting, like probably just stick to something even smaller. Like I just did this because it was something I genuinely wanted to create. But like if you're trying to create something that's grandiose that you don't really have a good reason to care about, then it will probably be quite hard to follow through. And also keep in mind that a lot of what I discussed in this video sort of like organically falls into place as you work on an app. It's not like I pre-planned all this out and just went ahead, coded it, and was done. Like, I did my best to plan, but I also went through multiple iterations, had to research multiple things. And yeah, but like basically aside from that point, I definitely suggest building projects as a way to learn if you have the time. I think it's one of the more difficult, but also one of the more fun ways and useful ways to learn. So if you have the time, I'd certainly take advantage of it. And yeah, thanks for watching.